Hi everyone, I'm Simon Vermeer. I work at Cirrus as a design engineer. For those who don't know Cirrus yet, actually we are an innovation center within Belgium, and we guide companies with technological innovation. We do this in different domains like ICT, materials, mechatronics, and advanced manufacturing. And I'm working within this group more specifically on additive manufacturing. Today, I will tell you more about materials for additive technologies. So, as all of you know already now, there is not just one technology. There are a lot of technologies, as you can see on this slide. And today, I will speak more about all the materials and the difference in materials between those technologies. So, if we start with the material itself and we look at the machines, we see that we can have different sources to manipulate the material. We can have laser sources, we can have a printhead which is printing the material, we can have a heated nozzle, an electric arc, and so on. And if we look at the materials, we can print metals, polymers, ceramics, composites, even plaster or paper. And those materials can be in a liquid state, a powder state, a wire state, or a sheet. Today, I will look with you at some of those technologies, and we will start off with stereolithography. What is this technology? Actually, we will print within a liquid with a laser source, and we will polymerize the material by this laser source. So if we look at the materials for this technology, we work with a photopolymer. This can be an epoxy or an acrylate. And this material can be a plastic, a composite, or a biomedical material. What is the advantage of this technology and this material is that we can print with a very accurate tolerance. We have a very good surface quality. We have some polymers available which can reach very high temperatures, up to 300 degrees. And we can even print in transparent, flexible, or castable materials. What is a little bit contra to this technology or this material is that support structures are printed in the same material. We will see more about this in another video. And because we work with a photopolymer, the material can degrade under sunlight. So actually it will lose its properties. As we are working with an epoxy or an acrylate, we need a chemical product to clean the parts afterwards. We are working with epoxy, so we risk to have an allergical reaction. And as it's not an industrial material we are printing like ABS or another material, it's more like a material-like material. The properties are comparable but not the same as those traditional polymers. Here you can see some examples of parts. On the left, you see an example of a biomedical implant, for example, which is printed in hydroxyapatite. In the middle, you see a part with the support structures, and on the right, you see at the bottom a part printed at materialized mammoth printers. Those are the biggest printers which exist for this technology. And on the top, you see another example of the printing process. Then we come to another polymer technology, fused deposition modeling, maybe the most known technology. With this technology, we feed a polymer filament through a heated extruder. And with this molten polymer, we will print on top of a platform and later on the part itself. Which polymers are available for this technology? In fact, we have a wide range of thermoplastics, and actually every material which exists in a wire, we could print with this technology. The most known are PLA, ABS, polycarbonate, polyamide, and Ultem, which is more suitable for high-end applications. The advantages of this technology and those material is that with newer technologies, we can use pellets instead of wires, which will widen the material range even more. Materials are still under development, so every year or month there are coming new materials. We can combine different materials if we have more than one nozzle. As with stereolithography, we had the support structures in the same material. We can use with FDM another material to print the support structures, and those supports can be dissolvable afterwards. This technology is rather clean, so you can use it in an office environment. But it's rather slow compared to other technologies. For more massive parts, we have quite a rough surface finish. And as we are working in layers, we have more anisotropic mechanical properties with this technology. Here you can see some different materials which are available. The most known at the bottom of the pyramid are PLA, polyprop, and so on. The more engineering plastics are right above, and then as high performance materials we have the PEEK or the Ultem materials. And on the right you can see a comparison between all those materials on certain topics. Here you can see on the left that we can print in different colors. On the middle picture, you see the part we want to print in white. The black material is a support material. This is soluble in water or in water, so it's easy to remove it afterwards. And then on the right, you see an example of a more office kind of machine. Then the next technology, we have material jetting. Actually, this technology is quite comparable to a printer you have at your home, at the office, because we will print the material with a print head. This material is also a photopolymer, so quite similar to stereolithography, but we will print with droplets of material. And those droplets will be photopolymerized by a UV source right after printing. This is a very accurate technology. We can achieve high surface quality with very fine details. We can combine different materials in one part. We can combine different colors, but we need a lot of support structures. We need chemical products to clean those parts. We are again working with an epoxy, so we risk to have allergical reactions to the material. And the material is very expensive. Also, the lifetime in which we can keep the materials is rather limited, 6 months to 1 year. And similar to stereolithography, the material ages during time, so when it comes in sunlight or we manipulate the part, it will decrease in quality. Here you see some examples of this technology. So we can print on the left in different colors, even combine it with transparent material. On the bottom you see a part which is printed in one. The white material is rigid, the black material is flexible, so we can combine it. In the middle you see a prototype for an injection mold, so we can make prototypes for injection molding, which we can use for several shots, and then afterwards we replace it by a conventional mold. And then on the right you can see an example of electronic circuits, which are also printed with a technology which is similar to this one. Then we come to the next technology, binder jetting. This is one of the technologies we use to print powders. How does it work? In fact, we spread a layer of powder, and this layer of powder is afterwards glued together with a binder. After this step, those printed or glued powder parts are taken out of the printing bed, and they are infiltrated with a second material. So if we look to the available materials, we see that we actually always have a combination of two materials. For example, a stainless steel or a tungsten, which is infiltrated with bronze material. What is a big advantage of this technology is that we have rather good mechanical properties. We can machine also those metal parts. And if we compare it to laser-based technologies, this technology is quite cheap, also quite quick in printing, because one of the reasons for this is that we don't need support structures, and thanks to this, we also have a great design freedom. But as you can see on the available materials, the materials are quite limited. There are also more porosities in those parts than in parts made by other metal technologies, and we have a very rough surface finish. Another example of binder jetting is printing of plaster. So same technology, but instead of metals, we will use plaster material, which is very cheap for printing full color parts. I will show you an example afterwards. It's also a very fast technology, which is perfect for demonstrators. On the other hand, those parts are quite brittle and only suitable for visual prototypes. The parts have a rough surface and most of the time also a poor accuracy. But as you can see on those examples, we can print a complete part full color. So the part on the left is printed in once, so we don't need to assemble it afterwards. But if you let it fall on the floor, it breaks. Then we come to another polymer technology, selective laser sintering. With this technology, we will melt polymer powder together. So again, we will spread a layer of powder and we melt it together with a laser source. Some available materials are polyamide, different grades of polyamide, also fire resistant or filled with glass beads. We can also combine the polyamide with aluminium, so we get alumide. And then we have also a flexible polymer available, which is TPU. A very big advantage of this technology is we don't need support structures, so we can print very complex parts. We have good mechanical properties, but the surface finish is quite grainy, quite rough compared to the previous technologies we saw. We have anisotropic mechanical properties, so the properties are good, but we have to take into account that they might not be the same in all directions. And the material range is quite limited compared to, for example, FDM technologies. Here you can see some examples of parts. So the parts are printed in a cake, as you can see on the right side. We can print flexible interlocking parts, like you see in the middle. Then we come to the next technology, which is laser beam melting. Again, a metal technology. with this technology, which is quite similar to selective laser sintering, we will again spread a layer of powder in metal, and we will melt the powder particles together to make the part. If we look at the available materials, we have all kind of aluminium alloys. We have some titanium alloys, some steel alloys, and some nickel-based alloys available. What is a big advantage of this technology is that we can print a rather broad range of materials, especially if we look at metal technologies. And of all the metal technologies, this is the technology which can print the highest details. A disadvantage of this technology is that we have high thermal stresses within the part, so we will need a lot of support structures, which we will discuss in another video. Here you can see some examples of parts. So a complex heat exchanger at the bottom, a building plate on the right with some parts of a bike frame, and on the top you see a setup of the machine in an industrial environment. Then we come to electron beam melting, again a metal technology which is similar to selective laser melting. But with this technology, we work in a vacuum. So this makes that the materials are quite limited. We can print titanium alloys, cobalt chrome, even copper, which is under development now. A big advantage of this technology is that we have very low porosities because we are working in a vacuum. We can stack parts on top of each other, which is not possible with selective laser melting, for example. We will need less support structures, and because the thermal stresses within the part are rather limited. What is a disadvantage or a limitation of the technology is that we can not print as many metals as with the other technologies. We can only print or use conductive materials. We will have a rather rough surface quality of the parts. And because of the powder which is around the part is also sintered, it's quite hard, or it can become quite hard to take the parts out of the cake. Then we come to, I think, the last technology, which is lasercladding or WAAM. Those are two technologies which are quite similar to each other. In fact, we feed a powder or a wire through a nozzle, and we will melt it by using a laser or an electric arc. Which are the materials available for those technologies? If we work with laser cladding technologies, we use metal powders. If we use WAAM, it's material existing of a wire. Examples of materials are stainless steels, Invar, titanium and aluminium alloys, and also nickel-based alloys are possible to be printed. This technology can be multi-axis, so we can print rather complex parts. We can use a wide range of materials. We can also combine those materials, which I will show on the next slide. And we can print in a normal atmosphere, so we don't need a vacuum or so on. For some materials, we will need, for example, a shielding gauze to protect the material during printing. What is a disadvantage of this technology is that it has a rather poor accuracy. You will see the layers a lot, so we need to machine the parts afterwards. We cannot print very complex parts compared to other technologies. And during the printing process, we can have some high thermal stresses within the part. Here you see some examples. On the top, you see a printed part before and after machining. So before machining, it's very rough. After machining, it looks very nice. And on the bottom, you see a part which is printed out of multiple materials. So at the bottom, we use an Invar, and at the top, we use a steel. And actually, by combining those two materials, we will have different properties within the same part. And as a last slide, I would like to give you an indication about the cost of additive manufacturing materials. So you can compare it to conventional prices. The most important ones are, for example, titanium, polyamide, and then the photosensitive resins, which are quite expensive compared to, for example, the ABS filaments, which we use for FDM. I hope you enjoyed this webinar. If you have more specific questions, you can always contact me by mail or by phone. And I hope to see you again in the next video.